I hope you can hear me. Perfect. Hi, I'm Rishabh. Today I'm going to talk about a compiler-based defense for these data memory-dependent prefetchers. Let me first start with the traditional prefetcher attacks. In these attacks, what happens is that if the address is somehow dependent on the secret, then you can probably leak it using a cache-based side channel using a prefetcher. But what has changed is that these attacks no longer can break the constant time programming, because in constant time programming we make sure that none of our secrets becomes none of our addresses become secret dependent. Instead, now we have these new type of prefetchers that not only prefetches what's the next address, but they also use the data, and they use the data to prefetch it again. See this for loop where you have sum plus equals to, and it's a pointer chasing loop where you take what's inside this array and you consider that as an address, and then you try to fetch data at that address. Now, what these prefetcher do is, these prefetcher are no longer secure from constant time programming, because your data will actually be sometime be secret. You cannot say that your data will never be a secret. It needs to be a secret sometimes. So how do we protect against such threat? Our core intuition lies on this fact that we have studied some of these prefetchers, and what we have realized is that before making this fetch where they take the data and consider it's an address and give out the fetch, they check is it a valid virtual address. It's important for them to do so for performance reasons. What we say is that suppose if we can somehow ensure that no data in the memory looks like a valid address, or at least no secret in the memory looks like a valid virtual address, then what happens is that these prefetchers cannot fetch it, it never goes to the cache, and our secrets are never leaked. So imagine if we have the secret, what we actually do is we break the secret into, we break the 64-bit secret into two 32-bit segments. And in both of these segments, we paired some constant value such that because of this constant value, the 64-bit aligning data in the memory is never a valid virtual address. Something like this. The good thing is that we don't care about registers at all. So for doing this transformation where we say that the data inside the memory should be in this particular format, we don't care how the data is in the register. The data can be in the register in the original state, so all the instructions that take data from the registers are unaffected. So what we actually only have to do is we just have to ensure that when we store our data into the memory, it gets broken into this format, gets padded up, and gets stored in the memory. And when we load it, we combine the data correctly and get into a register and do the operation the way we should be. And we do it for different sizes of these data, right? Like for example, if you have a 64-bit data, we definitely need 128-bit of space because we need to split it into two 32-bit chunks and then put some padding, put a constant suffix behind both of the chunks. But suppose if it's a 32-bit data, we just say that for a 32-bit data, we need a 64-bit space to save it with the constant prefix that we have. Similarly, if we have a 4-bit data, we say that because the thing that is unsafe is that these prefetcher looks for a 64-bit aligned data in the memory that looks like a virtual address, and that is what we don't want it to be. So okay, so in a nutshell, what this defense is that the compiler ensures that every secret that is stored to the memory, which looks like it never looks like a virtual address. So now these DMP, these data memory dependent prefetchers, never fetches for them, and it's never leaked. This works across various type of DMP implementation, because this is one of the basic assumptions that these implementation makes, that, oh, if we are going to fetch our data, it better looks like a virtual address. And there are ways to disable DMP, like there are chicken bits, but what we do is we say that we only do it for secrets. So sure, it's a lot of pain to only do it for secrets inside the compiler, but also there's this hypothesis that if you just do it inside the compiler, then you can have all of your code that is not secret is still using still can be using all the performance benefit that these prefetcher brings in, but but all the secrets that can be leaked by these prefetchers are now secure. This mitigation was implemented inside LLVM in our personal fork of LLVM, not upstream. And this was pretty complex compiler engineering, and I'll go through some of the steps that we taken to implement it. So the first thing that we care about is how do we annotate secrets? Interestingly, for this mitigation, we care about increasing the storage. We care about increasing the storage size for each secret. So what we cannot do is we cannot do a taint analysis and say that these are the instructions that is tainted, because we are not trying to transform the instruction, we are actually trying to transform the memory. So our annotation work on the allocation level. So we have ways where you can annotate the heap by using our custom allocator. So what happens is that if you use our custom allocator in the heap, we will provide that extra storage. We will do we'll provide the extra storage. We will do the runtime stuff for keeping track of the other parts where they are saved. Similarly, for stack, we implemented a small pass inside LLVM so that because the stack allocations inside LLVM are like pointers, at least when they are at LLVM IR level. So we implemented a pass such that we just treat it like a heap variable for some time. Similarly, we do the same thing for globals as well. And once we know that sure, like these are the secrets that we have annotated, the next thing is how do we keep track of the loads and stores that are connected to these allocations. So suppose we have some memory allocated, and now we want to actually transform the load and store that will actually do the splitting of the data and combining it back to use it. How do we track it? And I have worked on points to analysis, and we all know that static analysis is not precise enough that it can exactly tell you that this load is for this particular allocation. It cannot do it 100% of the time. So we needed something dynamic for this. So what we actually do is we set the top bit. One of the domain top bit that is not used in addressing, we set it and we keep track of it in the whole program just to know that, oh, is it a secret or is it not a secret? The next thing that we do is for every store and load, we transform it with this guard where we just check like is the secret bit set for this or not. If it's set, then we transform that store. A similar thing we do for load, that if this bit is set, that we transform the load. These transformations, what they actually do is these transformations actually inside LLVM IR are compiler passes which goes through the secret and breaks it into these chunks, masks the constant suffix and stores it back into the memory. So now what we are left with is this, that if this was the original memory, then we save it in a way that we just save the 32-bit chunks in the original memory, and this dark area is the constant suffix that we use to say that we use to make the prefetcher believe that these are not the valid virtual addresses. But then we have this extra memory. Now this extra memory is like a shadow memory which we keep track in our runtime, and we use these both value. We combine them when we have to use the registers. But this is not all about it, because compiler also adds some memory operations, and which are much more trickier to handle, because what we have seen so far is that these are the memory operations that got generated from the things that were in the user program, that the program that we were compiling. But then compiler does a lot of different kind of things. For example, your callee save registers, your register spills, your arguments that are passed through stacks. Now there is no known attack which uses these compiler generated memory operations for leaking secrets using DMP. But to be robust and to be forward looking, we have also implemented support for this. And this support, for supporting these things, we had to do two things. We have to first increase the size of the allocation. Like that's our basic thing. We need more memory. And the second is we transform the load and store. Now these things are done by the compiler. So if I give you the program And if I have a compiler, I cannot beforehand decide how much more memory I want, because I don't know when the spill will happen. I don't know I might know what are the arguments that will be passed through stack, but I definitely don't know when the spill will happen. So what we did is, we handled all of these ad hoc cases after the register allocation. So wherever memory for these are allocated, we make sure that we double that memory, or we do whatever with that memory, so we have that extra storage for the other half of the things. And this means that changing the calling convention. So inside the compiler, I updated the calling convention completely, so that the calling convention now supports this, the extra storage that we need. And we do it after register allocation, so it means that we don't have any kind of scratch space, or like we don't have anything, because all the registers are allocated. So we reserve some registers, which also give performance impact, but also limits us what we can do with these transformations. And these things happens at various different places inside the compiler. If it was an instruction transformation, we could have written just one pass, and that one pass could have handled everything at the end. But since we have to change the allocation, we have to keep track of everything that is going inside the compiler. Inside the compiler, we also cannot set high bits. Like I cannot set a top bit of the memory that is allocated for a register spill, right? So I have to manually keep track of the load and store that are attached to it, because I know where they are happening. And with all of this, what we result in are a lot of overheads, because now each store is being converted into a lot of stores, and each load is being converted to a lot of loads, and there are so many conditional. Is it a secret bit? Is it not a secret bit? We result in a huge overhead, but it is secure. And like, this is one conclusion I want you all to take it from here, that in reality, the compiler engineering at this level is extremely intense. And like, there were times where I wish that there was something simple, like a simple hardware primitive, like maybe I could have been able to set these chicken bits from the user code or something like that. But we pushed the design as far as reasonably possible without them, to actually evaluate how much protection can we achieve in absence of anything like this. Like, these things are still these things still act as the stop gap solution for older hardwares, for things that are not actually supported by the vendor, or things that actually cannot be fixed. With this, I can take some questions.
Thank you. I think I will ask the first question. Did you also compare with just disabling the DMP? And also, I think efficiency cores do not have DMP. Also, you could just run on efficiency
No, correct.
cores.
I think so. We didn't do this. We didn't disable the DMP, and we did not run the experiment. I think the actual reason is that the attacks that we have, right, like, they are so fragile that even if we disable the DMP, we don't know that was it the DMP that disabled didn't make the attack go through, or was it our stuff, right? And about these cores, right? Like, there are these cores where the DMP is not enabled by default. I agree. Like, I think we also mentioned it somewhere here that or use the core which don't have such prefetchers. But we wanted to give a a robust protection that it works on anything.
Questions?
Thanks. So I was just curious, did you consider something like XORing the secret with some random value and storing it, as opposed to splitting it into two locations, and why do you prefer this way?
Can you repeat it? I missed the first part.
I was saying another option here to store the secret in a way that doesn't look like a pointer would be to XOR it with some random value and still use the same storage space. So why do you prefer this version?
Correct. No, I see what you're saying. I think, let me just think about it, because we went through this. Why can't we just XOR things, right? Like, there are these data masking techniques, right, which actually exactly does this thing, right? But I don't recall the reason right now. Yeah, but there was a reason for that.
Any other questions?
Thanks, cool work. You had some pseudocode on one of your slides, which came down to if the secret bit is set, then this, else that. it was not entirely clear to me if you compile this to straight line code or if you keep this if branch. And if you keep this if branch, does that not introduce speculative leakage of some sort?
No, correct, that's correct. Like there is this thing that the transformations that we are doing, are these safe? Like do they add any more side channels or not? So what we have done was we manually checked a few things. We made sure the compiler flags are fine. But eventually what we need is that we need some sort of two things. We need some sort of formal verification on the side where we can model these transformation and say that they can never leak stuff for a given set of things. Versus we also need some decent understanding of how these compiler paths are working. So what we did was we made sure that the flags that we use right now were the flags that were popular among the like the normal constant time compilation pipelines.
Okay, so wait, so do you compile it to straight line code or not? Like, do you compile it to a CMOF or something like that, or you just keep it to the conditional jump?
No, we compile to CMOV.
Okay,
Yeah.
okay, makes sense.
Yeah.
Thank you.
Questions? One more question. Is it possible to have a version of your compiler path that doesn't need secret annotations without any manual annotation of the secrets?
Can you repeat that?
Is it possible to have a version of your compiler path that doesn't need secret annotations, like completely automatic?
I think it's possible. I think it's possible to implement an analysis like that, like which is a little over-optimistic and does more things. I think it's possible. We just didn't do it because it will be a lot more effort to have that kind of a taint analysis in place.
Okay.
Yes.
Thank you. Let's thank the speaker.